Hello everyone, very quick lesson on lesson 6.3b on non-conservative forces. Essentially what this is saying is that sometimes energy appears not to be conserved, and usually this is in a non-isolated system. So first thing we're going to do is we're going to define a non-isolated system, which is a system in which energy can cross its boundary. Okay, now the total amount of energy in the universe is conserved, right? However, this device or whatever we're looking at is not isolated, which means that energy can come in or energy could be coming out, such as a pot with or without a cover on a stove with boiling water. In this case here, right, you've got your pot, you've got your boiling water, it's heating up, energy is going into the system. It's coming through this way by radiation and potentially even some conduction. And so if your system that you are considering is just the pot of water, this is non-isolated because the amount of energy that this pot of water has is not going to remain constant. So let's take a look at an example of what this might look like actually within our physics. We've got a 0.4 kilogram hockey puck that is shot up a ramp, right? So hockey puck, it shot up a ramp, 15.6 meters per second, reaches a height of 0.80 meters. And the question is, first of all, how much energy was lost and what is the percent efficiency? Well, in order to find out how much energy is lost, we're going to need to, first of all, figure out how much energy there was to begin with, which was kinetic energy, 1/2 mv squared, which is 1/2 times 0.4 times 15.6 squared. And as you do that calculation, you'll find that 48.67 joules of energy were there at the beginning. Well, how much is there as this puck reaches the top of the ramp? Well, this kinetic energy has all become potential energy. And so EP is equal to mgh. So the mass, again, is 0.4, acceleration to gravity 9.81, and 0.8, which means the potential energy here is actually only 3.14 joules. Hey, look, pi. Fun. Anyway, so how much of this was lost? Well, that's going to be the 48.67 minus the 3.14, which means that 45.53 joules are, and I'm putting lost in quotations because it's not really lost. It is actually just exited the system that we are considering, this non-isolated system. However, if we took the energy that's remaining in the system as well as potentially where it is, and this probably has gone into the form of work against friction, which means it's actually probably in a thermal store right here, and actually probably hasn't even left the device. It's just that we haven't been able to calculate, and that's why we say it's lost. That is an accounting error on our part rather than anything else. Sometimes you see the formula look like this, which is very similar to what we've done before. Where this W is just the work against friction or lost energy, and again putting that in quotations because it's not really disappeared. It's just that we can't account for it within our particular accounting system of kinetic and potential energy. Now the question also asks to find the efficiency. So if we're going to do that, efficiency is going to be the output that's desired divided by the input times 100%. So 3.14 joules, divide that by 48.67 joules times 100 means the efficiency is simply 6.5% to 2 sig digs. Okay, hope that helps. Thanks for watching.